How does an airplane fly? An ocean of air surrounds the Earth, and an airplane moves through the air. It's the air that keeps it up. So, to learn about flight, we must learn about air. We can see the effect of air in many everyday things. The pressure of moving air blows the smoke from chimneys. Air prevents light objects from falling straight to the ground. A flag is blown back because air resists its forward movement. In water, we can see the same kind of thing. Water drags at a piece of cloth. Flag. Water resists the fall of a disc. Air resists the fall of a sheet of paper. A mine will float in water. Barrage balloons float in the air. In fact, air and water behave very much alike. But although a seagull can float at rest on water, it cannot stay up in the air without moving through it, so that the air flows round its wings. The way the air flows over and under the bird's wings causes the upward pressure, or lift, which enables it to keep aloft. And it's a similar flow of air round an airplane's wings that lifts it up and makes it fly. Since air and water behave very much alike, if we look at colored water flowing, we can learn about airflow. The water flows through the narrow part of the tube very much faster than through the wide part. Here's an easy way of seeing why this happens. Using benches to form a narrow gap, a group of boys keep their pace and formation on either side, but they have to move faster through the narrow part. Water does the same kind of thing. A machine forces a stream of water filled with particles to flow past a glass window. A narrow gap is put in. By watching the particles, we notice the speed up of flow through the narrowest part of the gap. Any flow of water exerts both a forward and side pressure. If water is made to flow through an ordinary glass tube, which has a hole in its side, we see there is forward pressure by the way the card is pushed aside, and we see that there is side pressure by the spurt of water from the leak. If we put pressure gauges in the first glass tube, they show there is a much lower pressure at the narrow part than at the wide part. The faster the flow, the lower the side pressure. This is called the Venturi tube. Air behaves in a similar way. If we connect the Venturi tube to an air cylinder, the air speeds through the Venturi, and its side pressure becomes much less than atmospheric pressure. The water rises in the U-tube, pressed up by atmospheric pressure outside the tube. When there is no airflow, the two levels in the U-tube become equal because atmospheric pressure inside and outside is the same. Much the same happens with a piece of paper. When held like this, air pressure on both sides is the same. Its own weight makes it hang down. When the man blows, the paper lifts up because the air above it flows forward, reducing side pressure. Atmospheric pressure under the paper pushes it up. When air flows through air as through a tube, pressures can be changed. Two sections of metal form the top and bottom of a Venturi. A wind machine sends a column of air through it. One section has holes along its inner surface, connected to metal tubes underneath. These are joined by rubber tubes to a series of pressure gauges, which indicate how pressures vary in the Venturi. So long as there is no airflow, the water levels remain equal, because the atmospheric pressure everywhere is the same. When the wind starts, the air flows through the Venturi and over the holes in its surface. As the air flows forward, its side pressure becomes much less. The colored water rises in the pressure gauges. The highest level shows where the pressure is most reduced. This is where the gap is narrowest, making the air flow faster. If we could see the air flow in the Venturi, it would look like this. The top half of the Venturi is replaced by a flat plate. The air flowing on either side of the Venturi now does all the work of narrowing the gap and speeding up the flow, and there is a reduced pressure over its top surface. We can remove the flat plate altogether and see that there is still a reduction in pressure. The air itself, flowing where the flat plate was before, becomes the inactive side of a narrow gap. Compare the Venturi section with the section of an airplane's wing. They are similar in shape. An airplane's wing is so shaped that when it is moved forward at a slight angle, the air flows over its top surface at an increased speed, as it would over the lower half of a Venturi. A wing section placed in the water flow machine shows the speed up of the particles over the front or leading edge and the topmost part of the wing. This flow reduces pressure on top, and atmospheric pressure underneath lifts up the wing. Just as the paper was lifted when the man blew over the top of it. It must be remembered that it is the top of the wing which plays the most important part in flight. It is the increased speed of flow over the top surface which reduces pressure and creates lift. The underside plays a small part too, as will be shown later in the film. A wing section, made like the Venturi with holes in its surface, can be connected to the pressure gauges to show the pressures on the wing when air passes over and under it. The holes on the top surface are connected to the 4 left-hand pressure gauges. The wind starts. The colored water rises most where airspeed is fastest, at the highest point on the top surface. To reduce the pressure even more on the top surface, the angle of the wing is increased. Put a wing section in the water flow, increase the angle, and you can see the speed up in flow. The way the liquid has gone up indicates there is less pressure. There are holes on the underside of the wing, which can be connected to the 3 right-hand pressure gauges. Since the wing is set at an angle to obtain lift on its top surface, air must strike the underside. This airflow is slowed down, causing an increase of pressure. The water in the right-hand tubes is forced down, showing this increase in pressure on the underside of the wing. With the wing at any normal flying angle, then, not only is the pressure on top reduced because of the speed up of flow, but underneath the wing the pressure increases slightly above normal air pressure because of the slowing down of the flow. It is because the moving wing changes the pressure of the air around it that the airplane can fly. A wing section attached to a balance shows how angle can affect the lift, even though the airspeed remains the same. With the wing at 0 degrees, it will lift 2 weights and remain balanced. Increase the angle to 5 degrees, and it will lift 3 weights, because although the main airflow is the same speed, the airflow over the top of the wing has become faster, and pressure is more reduced. Therefore, an airplane increases its angle when it wants to lift a greater weight, or if it wants to lift the same weight but fly at a slower speed, such as in landing approaches and contacts. At too great an angle, lift begins to fall off. The wing has reached what is called its stalling angle. At this angle, the airflow over its top surface breaks down. A wing section in the water flow, brought to the stalling angle, shows that particles no longer flow smoothly over the wing, but become restless and turbulent, even creeping up the wing from back to front. When an airplane reaches the stalling angle, lift decreases and it drops away. So an airplane flies at any angle less than the stalling angle, according to its speed and load. Lift is the force that supports the weight of the airplane. It comes from changes in the air pressure caused by the airflow. The airflow is created by the shape and the forward movement of the wings.